This video will contain two segments. The first segment is going to be all about percent composition. Regarding this learning target, I can calculate percent composition from lab data or standard information. And the second portion is going to be about empirical formulas and molecular formulas. Okay. So let's start out with percent composition. What exactly is percent composition? Percent composition is that if you look at a chemical formula or a molecule and you gather data about the mass proportions of each chemical within the substance, you can get something called percent composition, which is the percent composition by mass each chemical is within your overall compound. Okay. So here you have a pie chart essentially of two different compounds. One's potassium chromate, one's potassium dichromate. And you can see from the picture they both contain the same elements. Okay, they have potassium, they have chromate, and they have oxygen. But based on the percent composition by mass, you can tell basically how the structures are different, right? Dichromate has more oxygen by mass than just potassium chromate. And potassium dichromate also looks like it has more chromate by mass than the other ones. Now, from percent composition data, we can actually determine what the chemical formula is of a compound we're dealing with. And this is oftentimes how we end up discovering like what chemicals are in something. We can analyze what elements are present and get a relative percent of each element in the compound, and then from that you can get a chemical formula of your substance. So to start with, there are really two types of problems you can do. This first segment we're going to deal with how to get percent compositions, okay? Both from lab data and from chemical formulas, okay? Percent composition. Now, just the thing about percent, something to keep in mind, because percents come up a lot in chemistry. You know how to get percents. You're very familiar with this. And when we think about a percent, all you're really doing is trying to figure out what proportion of the thing you're measuring is per total of whatever you're looking at. Okay? So you always take some part of the whole and divide it by the total and then times it by 100 to get a percent. Okay? So a question to keep in mind anytime you're doing a percent problem in chemistry is, what am I measuring? Because the tricky part is usually to figure out what the partial portion is, what the numerator is, because the total is usually pretty self-explanatory. Okay? So for a percent composition problem, you will be given either numbers or you'll be given a chemical formula. And from the numbers, if you're given numbers, the numbers you're given will be your part. The total would be if you added all the parts up, and then you always times by 100 to get to percent. Okay. That might sound a little confusing. When we do an actual problem, I think it'll make sense. So here's an example problem for you to try. It asks you to calculate the percent within a compound if you have 29 grams of silver and 4.3 grams of sulfur. All these problems are going to deal with the percent by mass. Okay, it would be pretty simple to get a percent composition of something if we asked it by number, because it would just depend on the subscript. Doing it by mass is a little more tricky, but pretty simple in the end because we're going to use molar masses. If you're given the lab data, you don't even need molar masses. You just use what's given. Okay, to get a percent, you need to divide some partial portion divided by the total. So these are really our partial portions. What we need to get first is a total. Okay? So a total just means add up these two numbers, and if you add them up, you should get 33.3 grams of whatever this compound is. Now to get the proportions that silver is of the total and sulfur is of the total, you just take however much silver is, which is the part, and divide it by the total. And you take sulfur part and divide by the total. And then you also want to multiply by 100 to get it into a percent. If you do this in your calculator, 29 divided by 33.3 times 100 and 4.3 divided by 33.3 times 100, you should get that silver is about 87.1%, and that sulfur is about 12.9% of your overall compound. Okay. One thing you can always do at the end of a percent composition problem is double check that you did it correctly by adding up the percents. You should be able to add them up to equal 100, since your elements within your compound should contain all of the mass within that compound. Okay. So this is how to get a percent from lab data. How do you get a percent if you're given the chemical formula? What you're going to do there is you're not given any numbers, so you have to generate all the numbers. And the numbers we're going to base our problems on are the molar mass. Because if you want to know a total, right, we get the total mass of one atom, which would just be an AMU. But generally speaking, for chemistry, we work in moles and grams instead if we can. So to get a total, you're going to determine the molar mass of the entire compound. Okay, so that's your total. Just like last time, we got the total mass of the lab sample. And then you're just going to divide the mass of each element that contributes to the total by that total. Okay, just like we did for the silver and the sulfur. Then, as usual for a percent, multiply by 100 to get your final percentage answer. So let's try it. The question here, what is the percent composition of each element in lithium sulfate? Number one, we need a chemical formula. Okay, lithium sulfate, LiSO4. This has a charge of 2, this is 1. So there's my neutral equation. To get the percent composition, step 1 is determine the molar mass. So you take 2 times the mass of lithium plus sulfur plus oxygen to get your overall molar mass of this compound, and that will be your total. If we add them up, the molar mass is 109.936 grams. Next step is determine the percent of each element. So generally what I do is I list my elements. And remember, for percent, you're always going to take some part divided by the total. So we can already say for each of these math problems I'm going to set up, my denominator is going to be the total, 109.936 grams. The part in each case here is the part that the element contributed to the total. For example here, lithium contributed the mass of lithium twice because there are 2 of them. So if you add up the molar mass of lithium twice, times it by 2, you get that lithium is 13.88. There's just 1 sulfur, so this is going to be the molar mass of sulfur. And then there are 4 oxygens, so that 15.999 of each oxygen 4 times to get a final answer of 63.996. Get each to a percent by multiplying by 100. So 13.88 divided by 109.936 times by 100 gets you 12.63%. This one is 29.16%. And this one is 58.21%. Again, a good way to check your final answer is to add those 3% together to make sure you end up with 100%, because you should have all of your mass accounted for within your compound if you use all the elements in the compound. Okay. Note about sig figs. If you notice for this problem, all of these numbers are your molar mass. Okay. So technically, I got 6 sig figs going in. I could use all of them. If you look, a lot of them along the way are a little bit like this one's smaller and that one's smaller. So with this problem, it becomes very difficult to determine like how many of these are actually measured, because we're not even really dealing with measured quantities here. We're dealing with molar masses. So my general rule for percents is if you give it to the 100th, that should be precise enough to do whatever you need to do with your overall final data. So you notice all my percents here are to the 100th. If for some reason they're measured quantities from lab, then you would want to use significant figures from the measured quantities, which is why for the last problem, I ended up just with 3 significant figures in the end. Okay? So that's percent composition, either from formula or from lab data. The next segment of your video is going to deal with essentially doing these problems the other direction. Instead of giving you a chemical formula, I'm going to give you the percents. And from those percents, you need to figure out the empirical formula and sometimes the molecular formula if enough data is given to you. So number one, to do this, you need to know what an empirical formula is. Okay? And all an empirical formula is the lowest whole number ratio of the atoms within a compound. Okay? That's what an empirical formula is by definition. A molecular formula, the formulas we've been making for molecules, are not the lowest ratio. Remember, we didn't reduce those. They are the true representation of how the elements have come together. So if you look at this, really, ionic compounds are always empirical formulas because those are the lowest whole number ratios of the elements. Molecules, on the other hand, aren't empirical formulas. But with this particular problem set, we can only get empirical formulas out. So to get the true formula, you actually need a little bit more information, and I'll show you how that works. But for an example here, looking at that benzene molecule, C6H6, the empirical formula, the lowest whole number ratio, is just CH, and that's all the data that we could get out of this type of problem would be. If we needed to know that it was C6H6, we would need a little bit more data to deal with that. Okay, so we're going to do problems the other direction. We're going to get from percent to chemical formulas, and the chemical formulas that we produce using that method will always be empirical formulas. So they'll always be the lowest whole number ratio of the elements within the compound. How do we do it? Well, it's very similar to the problems we were just doing. Okay, we will be given percents, right? And those percents really can be, in the end, looked at as though they were masses, okay? In that, if we said, okay, I have 75% of this particular element within my compound. Well, if I had 100 grams of this sample, then 75% would be 75 grams, okay? If I have 20% of this element in the sample, if I had 100 grams, that would be 20 grams would be 20%. So choosing to say I have a 100 gram sample and therefore my percent equals grams is just an easy way to do these problems. The truth is you could decide you had any sample size. Okay, I have a 25 gram sample size. Well, then you would just have to go through and figure out, if I had 75% of this particular element in my 25 gram sample, how many grams is 75% of 25, right? So saying I have 100 grams is just an easy way to do these problems. So here's how we're going to do the problems. We're going to list out all the elements in the compounds. Next to them, I'm going to write down what their percents are, and I'm just going to change them to grams right away because it saves me a step. And now here's the trick, and that's why we learn this type of problem right now. I'm going to convert all of my grams to moles. Why am I going to do that? Well, because the data that's given to me is in mass. In the end, I want a chemical formula, and my chemical formula is not telling me relative proportion based on mass. Those subscripts that we generate were all based on counting, right? You'd have like 1 carbon to 2 oxygens in carbon dioxide. Now, by mass, the proportions will be very different between carbon and oxygens because the carbon atom and the oxygen atom mass differently. So to be able to use mass data to get a chemical formula from it, you make mass into mole. By doing that, we now have a count of each element within our compound rather than a mass of each element in our compound. Okay. Once we have a count of the number of moles we have of each element in a 100 gram sample, all we do is look at that count and we look at a ratio of that count. In 100 gram samples, if 2 of the elements have 3 moles and 1 of the elements is just 1 mole, then now you have a proportion of counting of 1 to 3, and you can generate subscripts from that data. Okay. So this problem type is the more complicated of the two problem types by far. And there's a lot of like, I'm not 100% sure of why she's saying to do it this way, but it works. And in class, I'll do it again for you guys so you see it. But we're going to do an example problem right now. Okay. So this is the example problem. I'm given percent data for barium, sulfur, and oxygen within my chemical compound. Okay. And from that, I want a chemical formula. So let's do it. So the first two steps, write down all of your elements within your compounds and write down your percents as grams. The next step was to take all these grams and make them into mole. Because right now we can't compare count based on mass because one of those things weighs more than the other two. Okay, so you have to get them to count to get a chemical formula. And the count we use in chemistry is the mole. Yes, 6.02 times 10 to the 23rd particle, but it doesn't matter in the end because 1 mole will be the same as 1 mole regardless of the identity of the element. So to get barium to mole, multiply, draw my line, gram per mole. I have a relationship between gram and mole, and it's called the molar mass. So the molar mass of barium, if you read the periodic table, is 137.33, 1 mole gram. Molar mass of sulfur, if you read the periodic table, is 32.06 gram per mole. For every 1 mole of oxygen, based on the periodic table, oxygen weighs 15.999. Now, you'll notice here these are just straight up their molar masses, not like times 2 or times 3, because I don't know the relative proportions. So all I'm trying to figure out right now is the count. How many moles of barium do I have if each mole is going to weigh 137.33? And how many moles of sulfur do I have if each mole is 32.06? So if you do this, you get numbers. So that gets me a count, a relational count for each of these elements. Okay. Once I have a count, I said you divide your lowest number. You take all of your big numbers and divide them by your lowest number. And that's just going to get me a relative proportion so that I know what my ratio is. So if I look at this, my lowest number is 0.4282. If I divide this number by this number, I get about 1. If I divide this number by this number in my calculator, I got an answer that was pretty close to 4. So what that says to me is this is a 1 to 1 to 4 ratio. Those become my subscripts. Okay. So then I have 1 barium to 1 sulfur to 4 oxygens. And you can see you generated a chemical formula that makes sense. Okay, you have barium sulfate. Barium is charged of +2, sulfate is charged of -2. Those actually balance out. And you got all that data from percent composition. This is what's done in lab a lot to analyze what a compound could be. I think we'll leave it there for this video. Okay, go on ahead and do the form and have a great night.